Excellent. Thank you, folks.
Once Sergi is here, we'll make Sergi co-host.
And you're going to do the recording, right?
Yeah.
So that's on your machine. Because yes, actually, I have to take my machine and go at the end of this, and it interrupts the saving of the recording. So you have to leave your machine on.
Okay.
Yeah.
Yes,
you
that's
can't shut down. It's a pain.
Yeah, that's a problem for me as well. That the last time I closed my laptop, and when I was leaving the room, and the recording got damaged. So I need to walk out in the snow with my laptop open from building to building to get back to my building. Okay.
Well, thank you.
I'm gonna go and see if our room is opened up yet.
Well, welcome everybody from all over the world, from Haifa, from Barcelona, from Nigeria. Excellent.
You still don't have a room here in Worcester. Okay. My cell phone died this weekend, and it's sporadically coming back to life, but it's very unreliable.
Okay, so if something screws up, I'll go to email instead of your phone.
Yeah.
But nothing's gonna screw up.
Nothing's gonna go wrong.
Hello.
Hello.
Sergi.
There we are.
Uh-huh.
Welcome.
Thank you.
You are now co-host, Sergi.
Okay. Great. So let me share this. Well, I guess I'll share it later. I'll just practice it, but I'll share it and then I'll share it again.
Okay, that'd be great.
I'll stop sharing, and then I think this allows you to share. Okay, so I can see the cover page of your slides.
Mm-hmm.
See the Acrobat frame, but nothing else from your laptop besides Acrobat and the slide. And now I have to move the thumbnail sketches off to the side here.
And okay, and there's the pointer.
Welcome, everybody. We have 10 screens active right now. And there's our speaker, Sergi Elizalde.
Mm-hmm.
Welcome, Lou. Welcome, John.
Yep, again, if folks, as you're coming in, if you could please just type into the chat room who you are, into the chat, who you are, where you are, and how many people are in your group. That would be super helpful.
Thank you, everybody. We're setting up the technology, and the talk will start in 10 minutes.
Mm-hmm.
And if you're looking for the chat window, if you use, on most machines, if you mouse over the bottom of your screen, you'll get a little menu will appear. You can try to the right or to the top on a Mac. I think it might be at the top, but that way you can find the thing for the chat window, and also the place to raise your hand if you need to get the attention of one of the organizers during the talk.
Okay.
I have to mute myself while I set up the audio in my classroom here.
Okay, well, I am unmuted just in case anybody gets bored. So it's all good. We'll be starting in a few minutes, folks. Bill's just going to switch classrooms and we'll take it from there. Again, if you've just joined us, if you could please find your chat window, the chat feature on Zoom. If you mouse over, I think the bottom of your screen, you should get a little chat button that you can. Yes, Darji, yes, you found it. Please let us know who you are, where you are, and how many folks are with you. And that would be a huge help. So thanks.
Okay, are we getting sound in here?
We're hearing you just fine.
Yes.
Testing the sound in my classroom. I don't hear anything coming out except for my laptop.
Because we're being quiet.
Peter, are you in New Hampshire or are you in New York?
I think he's in New York, but I will let him answer, but I don't think he's here.
Excellent, thanks, Pete.
Okay, I have audio.
All set up?
We don't have audio.
There's Pete.
We're out of time.
Huh?
We don't have audio. Do we have audio?
It's very quiet. I'm hearing something.
Oh, okay. Well, then that's probably enough to give feedback, and I have to shut it off. Let me check the audio again. I'll turn it back on after I do the introduction. Are we ready to go?
Yes.
Yep. Do you press the record button?
Okay. Yeah, I've been recording for a little while.
Oh, super.
Ladies and gentlemen, welcome to the virtual Combinatorics Colloquium for December 2019. This is sponsored by the Northeast Combinatorics Network with generous funding from the National Science Foundation of the United States. Your colleagues and friends can log in from anywhere in the world as long as they have this URL. So please spread the word. There'll be 3 of these colloquia in the spring semester we expect. And please stay in tune with our mailing list and our webpage on our YouTube site, our YouTube channel and our Google site. So we're very pleased that today we'll have Sergi Elizalde from Dartmouth College speaking to us on permutation patterns. So Sergi, after getting his degree at the Polytechnic University of Catalonia, came to MIT in 2000 and got his PhD under the supervision of Richard Stanley in 2004. And Sergi has held visiting positions at MSRI, the Mittag-Leffler Institute, the CRM in Spain, and the Memorial Sloan Kettering Cancer Center. And he's now a full professor in the Department of Mathematics at Dartmouth College. And we're very, very pleased to have Sergi join us. So please welcome Sergi, and I'll hand it off to him now.
Okay, thank you, Bill. So I'd like to thank Bill and Joe for organizing this and for allowing me to speak without having to travel anywhere. I guess the only difficult thing for me is that I tend to move a lot when I give talks. I tend to walk around. So I don't know how I'm going to do that. I also like to make jokes when I speak, and here, since I don't hear people laughing or not laughing, it's kind of weird to make jokes. So I don't know how that's going to work out. But let's see. So let me share my screen. So here are the slides, and I can get a pointer. Okay, there's the pointer. So what I'll be talking today is about consecutive patterns in permutations, and then a little bit in inversion sequences, and maybe I'll talk also, if I have time, about some applications to dynamical systems. So some of the results I'll talk about are old and some are new. And if I see some of you are people who've heard me talk before about pattern avoidance, so there may be some things you've already seen. But the way I aim the talk is to people who don't know even what anything in the title means. Well, okay, maybe permutations, you have to know what that means. But other than that, I'm gonna start with everything from scratch. Okay, so let's start with a basic definition. So we have suppose we have two permutations. So Sn here will denote the symmetric group of permutations. So I have a big permutation of length n and a smaller permutation of length m. So then we say that a consecutive occurrence of sigma of the smaller permutation in the bigger permutation is a subsequence of adjacent entries. So it has to be a subsequence where all the entries are next to each other that is in the same relative order as the entries of sigma. So here's an example. Okay, before the example, so you may have seen a similar definition without the word consecutive in it. So there's also such a definition, and usually that's called like just a pattern or a classical pattern. When people talk about occurrence, they may not have this requirement that the entries have to be adjacent. So in this talk, I'm gonna suppose that my subsequence of entries is adjacent, and I'm gonna call that an occurrence, and I'm not gonna be saying the word consecutive all the time, but that's what we'll assume I always mean consecutive occurrence. So here's an example. So if you take the permutation 4, 2, 5, 3, 1, it has an occurrence of sigma 1 equal 1, so 1 through 2 in here, because if you look at 2, 5, 3, these are in the same relative order as 1, 3, 2. So of the entries 2, 5, 3, the smallest one is on the left and the largest one is in the middle, just like in 1, 3, 2. Okay, then we could also have permutations that have more than one occurrence. For example, 1, 5, 2, 4, 3 has two occurrences of 1, 3, 2. It has one at the beginning, the 1, 5, 2, and then the 2, 4, 3 also are in the same order. So there are two occurrences. So this is the basic definition. And then we're going to say that pi contains sigma as a consecutive pattern, even though I'm not going to keep saying as a consecutive pattern each time. I'm going to say that pi contains sigma if it has an occurrence of sigma. And if not, I'm just going to say that pi avoids sigma. And then there's this notation that I'll be using. So Sn of sigma will be the set of permutations in Sn that avoid sigma. Okay, so for example, this permutation 2, 5, 1, 3, 4, I'm going to say it avoids 1, 3, 2, because even though it contains a non-consecutive subsequence in the same order as 1, 3, 2. So if you look at 2, 5, 3, there'll be a subsequence in the same order, but it's not a consecutive one. So I'm just going to say it avoids 1, 3, 2 in my terminology. Okay. Okay, so that's the main definition. Now, let me tell you a little bit about how consecutive patterns have been studied. So even before the definition of a consecutive pattern, people have been studying consecutive patterns without calling them that. So in disguise, there have been consecutive patterns in the literature. For example, you probably all have heard about descents. So descents, you can think of them as occurrences of the pattern 2, 1. So that's just a descent, and then these were studied by Euler back in the 1700s, and then the permutations that have a given number of descents is called an Eulerian number. There's another occurrence of consecutive patterns that has been studied, which are peaks. So if you look at peaks are just entries that are bigger than the two neighbors, and you can think of them as occurrences of 1, 3, 2 or 2, 3, 1. In a permutation, and they are used in algebraic combinatorics. There's this thing called the peak algebra and so on. Then there's also, you probably know about alternating permutations, which sometimes are called up-down permutations. These can be thought of as permutations that avoid the consecutive patterns 1, 2, 3 and 3, 2, 1. Because if you put these requirements, then the permutation has to go up, down, up, down, up, down, or down, up, down, up, down, up. And these were studied in the 19th century. And the generating function for these, the exponential generating functions are the tangent and the secant. So they are kind of fun generating functions. And then there's other, I guess, even before consecutive patterns, people also have looked at permutations according to increasing runs, which would be, in my notation, these would be occurrences of the increasing pattern. Okay, so these are some places where consecutive patterns have appeared in the literature, but then about 20 years ago, people started studying them systematically, like looking, for example, at all the patterns of length 3 and trying to count how many permutations avoid each one of them and things like that. So the systematic study started 20 years ago, even though they have been implicit in the literature for a long time. Okay. So here's some notation that I'll be using. So if we are interested in enumeration, we want to know, for example, how permutations permutations of a given length have a certain number of occurrences of a pattern sigma. So then we define this generating function that encodes that information. So here I have two variables, u and z. And one of the variables, the exponent of u is the number of occurrences of sigma in pi. And then the exponent of z is just the length of pi. So this is the basic generating function that counts occurrences. And it's convenient to make it an exponential generating function in z. So I put this n factorial dividing here. So that's the basic generating function. Then if I was just interested in the number of permutations that avoid the pattern sigma, then what I can do is just plug in u equals 0. And if I do that, if u equals 0, then all these terms cancel except for the ones where the exponent was a 0. So the exponent was a 0 if pi avoids sigma. So then I get that the coefficients of the generating function tell me the number of permutations of length n that avoid sigma. Okay, so these are the generating functions that we'll be interested in finding. Here's just a very basic example. If I take the pattern 2, 1, so now I'm just looking at descents. Then when I put u equals 0, this would be the generating function for permutations that have no descents. And there's only one permutation of each length that has no descents, which is the increasing permutation. So all the coefficients would be 1. And then, well, I'm dividing by this n factorial, but other than that, all the coefficients are 1. So this is just e to the z. And then if I keep the u and I look at permutations according to the number of descents, then what I'm getting here, these polynomials in U, these are called the Eulerian polynomials, and they count how many permutations of each length have a certain number of descents. And there's also a known formula for this generating function. It can be expressed in this nice closed form. Okay, so that's for the descents, but then we would like to do something similar, where instead of 2, 1, we have longer patterns. Okay. Also, feel free to interrupt me anytime. So I know this is complicated, more complicated with this system, but you have 2 options. You can either unmute yourself and talk, or you can, I guess you have 3 options. You can also raise your hand if you find the button, and you can also put a question in the chat window. And I think Bill is checking the chat window if anybody writes a question and I'm distracted. Okay. So if I don't hear, if nobody interrupts, I'll just keep going. Okay, so these are the kinds of questions that we're interested in. So one of them is just the enumeration question. So find formulas for these generating functions I talked about. Here's an example of such a formula. So I mentioned the one about descents, but there are more complicated ones that one can find too. For example, for 1, 2, 3, 4, the generating function for permutations that avoid 1, 2, 3, 4 as a consecutive pattern has this nice expression. Another kind of question would be not so much about finding the formulas, but about determining when 2 patterns are equivalent. And now by equivalent, there's a couple of ways you can define when 2 patterns are equivalent. Probably the most natural one is to say that 2 patterns are what's called Wilf equivalent. If we say that 2 patterns are Wilf equivalent, if the number of permutations avoiding one is the same as the number of permutations avoiding the other for each given length. Okay, so this is the definition. You can also write the same in terms of the generating function. That will tell you that the generating function when u equals 0 is the same for both patterns. Okay, so we call this Wilf equivalence, or sometimes weak Wilf equivalence. There's a notion of strong Wilf equivalence, which would be that we require not only that these generating functions are equal when u equals 0, but that they are equal for when you leave the variable u just like that. So so another way to interpret this is that 2 patterns are strongly Wilf equivalent if the number of permutations of length n that have k occurrences of sigma is the same as the number of permutations of length n that have k occurrences of tau for any n and any k. So not just there's the same number avoiding them, but the whole distribution of occurrences is the same. So these are the main 2 equivalence classes. There's another one that maybe I'll talk about later, but here's an example. So maybe before this example, let me say that there are some trivial cases where patterns are Wilf equivalent and strongly Wilf equivalent, which is when you, for example, when you take the reverse of a pattern. So if you take a pattern and then take the same pattern, but you read it from right to left, you're going to get 2 patterns that are strongly Wilf equivalent. And the reason for that is that occurrences of sigma in a permutation, if you reverse the big permutation, they will become occurrences of the reverse of sigma. So, and then there's some other symmetry you can do, which is, it's called complementation. So you replace, if the pattern has length m, you replace each entry I with m plus 1 minus I, and that also gives a strongly Wilf equivalent pattern. So you get some trivial equivalences, but then there are some other equivalences that arise that are not trivial. And here's an example of one of them. So if you take the pattern 1, 3, 4, 2, turns out that that's strongly Wilf equivalent to 1, 4, 3, 2, but it's not by any trivial symmetry that this holds, but it can be shown that it is true. And then when you look at longer patterns, then you get new kinds of Wilf equivalences. Okay, so this is the question of equivalence. And then there's a third type of question that people are interested in, which is about the asymptotic behavior of the number of permutations that avoid a pattern. So we may be interested in like how fast these numbers grow. So the number of permutations of length n that avoids sigma, as n grows, how do these numbers grow? And also we can ask questions about how they compare for different patterns. So one result in that direction is that if you look at the number of permutations that avoid 1, 2, 3, there's always more of them than the number of permutations that avoid 1, 3, 2. Now this is again, this is all for consecutive patterns. So if this was about classical patterns, then there will be an equal sign here. So in the consecutive case, this is true. Okay, so these are the kind of questions we'll be interested in. So I'll talk a little bit about each one of them. So let me show you, maybe I'll talk a little about the equivalence. So for length 3, you can check that of the 6 patterns of length 3, you have these trivial equivalencies that come from symmetries, and that's all. There's no more equivalencies. So there are 2 strong Wilf equivalence classes. Then you can look at the 24 patterns of length 4 and try to classify them too. And you get that there are 7 classes. So for length 4, all of this, well, most of these equivalences are because of trivial symmetries like reversal and complementation. But then there's one here, that's the one I mentioned before, that doesn't come from reversal and complementation. Now, if you're familiar with pattern avoidance in the classical case, not the consecutive case, then in that case there is only 1 class for length 3, and there are 3 classes for length 4. So this is pretty different, and it's not even true that being equivalent in one setting forces you to be equivalent in the other one. So the classes are sort of different. Okay. So that's for length 4. And now, of all these classes, the ones in green are the ones for which the enumeration is known. So there are formulas for the generating function for permutations according to the number of occurrences. But there are some of these classes, even for length 4, where we don't have a formula. Okay, so now if you look at these examples I showed you, it looks like all the equivalencies I showed you are strong Wilf equivalencies. Or in other words, for patterns of length 3 and 4, I didn't show any 2 patterns that were weakly Wilf equivalent, but not strongly Wilf equivalent. And turns out we don't have any such example of any pattern. So there's this conjecture by Brian Nakamura from 2011 that says that these 2 equivalencies are actually the same. So that if 2 patterns are weakly Wilf equivalent, so if the number of permutations avoiding one is the same as avoiding the other, then the whole distribution of occurrences is the same for the 2. So that's, I find this conjecture pretty interesting because, well, first because it's a little surprising, but also because it's been around for a while and nobody has been able to prove it or disprove it. Now we know that for patterns of length up to 6, it's true because we've classified them into equivalence classes and we get the same classes. And if you look at for lengths from 3 to 6, this is the number of equivalence classes that you get. So there are 2 for length 3, as we saw, 7 of length 4, 25 of length 5, and 92 of length 6. And then after that, we don't know we don't know what the classification is anymore. So in general, if I give you 2 long patterns, we don't have a good way to know if they are Wilf equivalent or not. Okay, so there's another reason why this conjecture is interesting is that there are other settings where there are similar conjectures. So one of them is about patterns in inversion sequences, which I may mention later if I have time. But there are others that are pretty unrelated, like you can define containment of words according to the generalized factor order. And then you get a very similar conjecture in that case that some sort of Wilf equivalence is the same as some sort of strong Wilf equivalence, and there's no proof in those cases either. So it's likely that whatever proof works in one setting may work in all settings, but we just don't know why this is true. Okay. So let me talk a little bit about how we find formulas for this generating function. So there are different methods, but one of them that's pretty useful is it's an adaptation of a method of Goulden and Jackson they call the cluster method. So it's basically some fancy version of inclusion-exclusion. So let me tell you what it is, because it's a pretty nice formula that they give. So so it's based on something that they call clusters. So a cluster is just it's something very simple. It's just a permutation that has lots of occurrences of a pattern sigma, and each one overlaps the next one. So each occurrence of sigma overlaps the next one, and you mark occurrences. So it's possible that there are more occurrences of sigma, but you don't mark those. So I mean, this is a little subtlety, but basically just think of it as a permutation with a bunch of marked occurrences of sigma that each one overlaps the next one. For example, this permutation here, this is a 3 cluster with respect to this pattern 1, 3, 2, 4. And the reason is if you look at the first 4 entries, that forms an occurrence of 2, 1, 3, 2, 4. If you look at the one starting with this 2, it forms a 1, 3, 2, 4. And starting with the 6, you get another 1, 3, 2, 4. Okay, so there are these occurrences of 1, 3, 2, 4 that overlap with each other. Okay, so now that we have this definition, we can define the generating function that counts these clusters. So this is a generating function with 2 variables where you count how many k clusters of length n with respect to sigma you have. And what the cluster method tells you is that if you can find this generating function c for the clusters, then you can find the generating function p for permutations. So here's what the cluster method is: a formula relating p and c, and this is what it says. So it says that if you have the generating function for clusters, if you just make this substitution, you put u minus 1 instead of u, and then you do this operation, then you get the generating function for permutations according to the number of occurrences.
Okay. Yeah.
Yes.
So I think we do have a question here.
Oh, okay. Let's see if I can open the chat.
No, that's all right. You don't have to. The question
Okay.
is 2, 7, 25, 92. Does the sequence have a nice pattern in the integer sequence?
Oh, that one. Yeah. So that's a good question. So we don't know. We actually have too little data here to find anything. So I put this in the OAIS, in the online encyclopedia, and there are 4 matches that start like this and continue in different ways. And I don't even know if, I mean, it may be none of those 4 matches if we were to compute more of this, which we haven't been able to. I mean, I guess for length 7, it's possible that with, you know, enough brute force, you can guess what this number would be. And then, but we don't really know anything about this sequence or any formula. Okay, so okay, so this the cluster method. So as I said, it tells you that if we can compute the cluster generating function, you can compute p, and it has a nice proof by inclusion exclusion, which I don't have time to do here, but it's actually it's only like 1 paragraph, so it's a nice proof. And
sorry,
yes.
Sergey, one more time. A question about the marked sequences. Does that mean that the lengths of the overlaps are predetermined?
Yeah. So when I define the cluster, so the marked sequences are part of the definition of the cluster, but they don't. So okay, I guess, how would I say it? So when I count here the number of k clusters, it's for all possible overlaps in all possible ways. Okay, so if I have One example would be if you have the pattern 1, 2, 3, 4, then the only way to construct a permutation that has occurrences of 1, 2, 3, 4 overlapping everywhere is to take the increasing permutation. But then, even then, you get to choose lots of ways for the overlaps to happen depending on what things you mark and you don't mark. So you still get a lot of different K clusters because you get to make choices for which of the occurrences are marked and which ones are not. Okay, so hopefully that helps. So they are not predetermined, but they are part of the definition of the cluster is that you get to choose where the occurrences are, where the marked occurrences are. Okay, so so here, once with this theorem, the nice thing about this cluster method is that computing the number of the generating function for the clusters is usually easier than computing. So usually counting clusters is easier than counting all the permutations, and that's how we are able to find this P in some cases. Now this is a definition. I'm just going to call the denominator here, I'm going to call it omega, and then this will be because in some of the theorems it will be easier to give equations in terms of omega than in terms of P. So just keep in mind that P is just the reciprocal of 1 over omega. Okay, so now, so I was saying that counting clusters is usually easier than counting all the permutations, and I'm going to try to convince you why that's the case. So so let's suppose I want to count how many clusters have, so how many permutations of length 11 have occurrences of sigma in these positions that I marked. So starting at position 1, starting at position 3, and starting at position 7. So if I wanted to count permutations that are clusters, then the fact that there's an occurrence of sigma starting at position 1, that's equivalent to saying that the first 5 letters are in this order. Okay, and then saying that there's an occurrence starting in position 3 would be telling me that these 5 entries are in this order, and starting at 7, the 5 entries will have to be in this order. Okay, so saying that it's a cluster is equivalent to this bunch of inequalities between the entries. Now there's a way to represent this with a poset. So what I can do is put the 11 entries and record what has to be less than what. So here this, when I put these edges, this is telling me that pi 1 has to be less than pi 3 has to be less than pi 5 has to be less than pi 2, but also less than pi 7, and so on. So I'm recording this as a partially ordered set. So then saying that the permutation has to satisfy all these constraints, it's equivalent to saying that it's a linear extension of this poset. So if you've never heard this word before, a linear extension is just an assignment of the numbers from 1 through 11, in this case, to the nodes of the poset in such a way that the order relationships that the poset tells you are satisfied. Okay, so here will be an example of a linear extension. So I assign numbers to the nodes of the poset, and that corresponds to having a cluster with respect to sigma, where all these conditions are satisfied. So that's a helpful way to interpret these clusters as linear extensions of posets, because sometimes we get some nice posets for which we can count the linear extensions. And that's how we obtain some of the formulas for the generating functions. So here are some of the results. So I guess the pattern, the most, perhaps the simplest pattern is when you take the monotone pattern, so 1 to up to m. Then, so remember this omega is the reciprocal of p. So this is the 1 over omega is giving me the distribution of occurrences of sigma. So the theorem is that this is the solution of this nice, I mean, I don't know how nice, but it's I find it nice enough differential equation. where here the derivatives are with respect to z. So I'm treating u as a parameter. And then there are some initial conditions that I didn't write, but they are pretty simple. So in this theorem gives this generating function, and for if you plug in u equals 0, then it gets particularly simple. And in fact, the solution for that has a nice exponential generating function, which was known already in the 60s. So before consecutive patterns were studied systematically, there was already this formula for the denominator of the generating function for permutations with no increasing runs of length m. Now, so maybe I should say the reason why we can do this pattern pretty easily. So actually, the original proof from 2001 that I found with Mark Noy is not using the cluster method. So we didn't know about the cluster method at that time. So what we did is we constructed some bijection from permutations to increasing trees, and then we counted increasing trees that don't contain certain configurations. But using the cluster method, it's actually easier to prove it, because in this case, all the clusters for this pattern are chains. So the poset that you get is just a chain, and then it's just a matter of counting how the occurrences can overlap, but it's not too bad, and you can find that. Now, the same method also works when the pattern, there are other patterns that are not the monotone pattern, for which the cluster posets are also chains. And here's an example of such a pattern. So if you have a pattern that looks like the monotone one, but then the entries s and s plus 1 are switched, turns out that the cluster posets are also chains for this pattern, and you can find some differential equation that it won't be this differential equation, but it will be something that involves s, but it's not that different from this one. It also works in that case. So there's some patterns that we can do in this way. Now, there's another set of patterns that can be enumerated, which is when we do non-overlapping patterns. So what I mean by that, so we call a pattern non-overlapping if the only way that two occurrences of sigma could overlap in a bigger pattern. So suppose you have two occurrences of sigma in a big pattern, the only way for them to overlap would be if they overlap in one position, but they cannot overlap more than that. Okay, so for example, if you look at this big pattern here, 3, 4, 6, 7, 1, 2, 8, 5, if there were two occurrences of this pattern in some big permutation, the only way for the two occurrences to be overlapping is if the 3 of one is the 5 of another. But there's no other way because of the way that they relate the prefixes and suffixes are. There's no other way they could overlap in more positions. So these patterns are particularly nice to work with, because then the cluster posets can be described more easily. And we have this theorem that says if you have a non-overlapping pattern that starts with a 1, then the generating function is the solution of this simple differential equation, where again there are some initial conditions that we know also, but I didn't write them here. So one example of this would be the pattern 1, 3, 2. So when you solve this, you get this generating function. So okay, so this solves the two classes, all the patterns of length 3, and then some of length 4. For example, these two patterns of length 4 are non-overlapping, so it gives the equation. There are some other patterns that are not non-overlapping, but there are similar methods that can be used to find differential equations. And then there's another pattern of length 4 that we can solve, but it's not included here, which is this one, 1, 3, 2, 4, for which there's a pretty ugly differential equation. So all the others so far were nice differential equations. This one is pretty ugly, but I guess we are happy enough that we have this. It turns out the proof of this theorem is nicer than what the answer suggests. So the proof uses the fact that the cluster posets for this pattern, the number of linear extensions is some combination of Catalan numbers. So there are Catalan numbers that show up in this proof, even though at the end the generating function satisfies a pretty ugly differential equation. And then the same method used for this one can be generalized to patterns that look like this. So basically this is like a monotone pattern, but then the 2 has been moved to somewhere else. And then you get some other variant of this. Okay, so these are all the cases. So for all the patterns of length 3 and 4 that I said were solved, they are covered by these theorems I mentioned. The other 3 cases, 3 classes of patterns of length 4 for which we don't have any closed form or any differential equation for omega. Now, for one of them, for 1, 4, 2, 3, we actually we're able to show that if there is a differential equation for omega, then there has to be some function for which we had a functional equation that would have to satisfy a differential equation, and we conjecture that there was no such differential equation. And this was later proved by Beaton, Conway, and Goodman. And is that so? One way to say this is that the generating function omega for the pattern 1, 4, 2, 3 is not definite. So that means that there is no, it doesn't satisfy any linear differential equation with polynomial coefficient. So in all the cases we had solved before, there was some linear differential equation with polynomial coefficients for omega, but turns out for this pattern here, there's no such thing. And for the others, we don't know, but it's also possible that there's no such differential equation. So that's a way to show that the generating function is complicated enough. There's also a lot of work in the analogous question for classical patterns. So you may have heard about this thing called the Noonan-Zeilberger conjecture that said that for avoidance of classical, so non-consecutive patterns, the generating function was definite. And that was the original conjecture by Noonan and Zeilberger. Later, Zeilberger made a counter conjecture. So he conjectured that his original conjecture was false. And then it's still not technically not proved either way, but Garrabrant and Pak showed that if you consider sets of patterns, so if you consider avoidance of several sets of patterns at the same time, then there are cases where that generating function is not definite. So that would be some sort of analog to what we found in the consecutive case. Okay, so this is about exact enumeration, and now I want to talk a little bit about the asymptotic behavior of permutations avoiding a consecutive pattern. So this is something we know about the growth of these numbers. So if you look at the number of permutations that avoid a consecutive pattern, if you divide by n factorial and then take the nth root, that limit is always a constant between 0 and 1. So if you know about classical patterns, you may have heard about the Stanley-Wilf conjecture that was later proved by Marcus and Tardos, that said that if you count how many permutations avoid a classical pattern, that number is always bounded by a constant to the n. So here it's different because for there are many more permutations avoiding a consecutive pattern because the condition is much less restrictive. So the number is not a constant to the n. In fact, it grows factorially, but if you divide by n factorial, then it is about a constant to the n, where that constant is between 0 and 1. Now this result was strengthened. Well, I guess this limit exists, but it's only known for a few patterns. This result was strengthened by Ehrenborg, Kitaev, and Perry, and they showed not only this limit exists, but actually the actual asymptotic growth of this ratio. So this would be I guess you can think of this as the probability that the random permutation of length n avoids the pattern sigma. So it actually behaves like a constant times a constant to the n, and then plus some lower order terms. Now, it's interesting that this result was proved using methods from spectral theory. And for a while, I was trying to find a proof that used like some classical analytic combinatorics, and I didn't get anywhere. So I don't know. It's interesting that the only way we know to prove this uses spectral theory. Okay, so this is about the asymptotic growth. Then there was the question about comparing the number of permutations avoiding one pattern with the number of permutations avoiding another pattern. So a question one could ask is, for which pattern of length m is the number of permutations avoiding it largest? So, in other words, like which is the pattern that's most easily avoided? Now, if you think about this for a while, you may have some guesses. I guess I'll just tell you the answer. So the answer is that for the monotone pattern, the number of permutations avoiding it is the largest. Now there is, you could think this is pretty intuitive. You could think that, okay, so I'm gonna try to give you the intuition why this is true. So, okay, so if you look at the total number of occurrences of a pattern of length m, the total number of occurrences in all permutations of length n, if you add the total number of occurrences, that will be the same no matter what pattern of length m you start with. So that's not hard to see. So if the total number is the same, the total number of occurrences, if you want a lot of permutations to avoid the pattern, then to compensate, there will have to be some permutations that contain many occurrences of it. So if there are many that contain 0 occurrences, there will have to be many that contain many occurrences. And for the monotone pattern, that's the one for which you can pack a lot of occurrences together. So there will be permutations that contain many occurrences of this pattern, and therefore there will be many that contain 0 occurrences. So that's sort of some intuition that gives that this should be the most avoided pattern. Now, if you thought the intuition was right, actually, well, you may think that it also works in the classical case, but it doesn't. So it's very surprising that if you think of the analogous result for classical patterns, so the non-consecutive case, if you look at which one is the pattern that's the most avoided, it's not true that it's a monotone pattern. In fact, it's very much not true. And there's not even a conjecture, or I guess it's not known what the most avoided pattern would be in that case. So it's nice that in the consecutive case we can have this result. Now there's a similar question for the which pattern is the number of permutations avoiding it the smallest, and in that case we also have this other pattern that looks a lot like the monotone pattern, but the last two entries have been switched. So it grows up to here, and then m and m plus 1 are switched. So for this one, the number of permutations avoiding it is the smallest. Again, there's nothing known in this direction for classical patterns. It's not known for which pattern the number of permutations avoiding it is the smallest. Okay, so that's about asymptotic behavior. Now, I'm gonna talk about a little bit about patterns in inversion sequences, because this is something new that my graduate student Juan Auli has been looking at. So I wanted to mention it a little bit. So many of the definitions are the same, but now instead of looking at patterns in permutations, we are looking at patterns in what we call inversion sequences. So let me tell you what an inversion sequence is. So an inversion sequence is just it's just an integer sequence where the ith entry is between 0 and I minus 1. Okay, so it's a very basic definition. And then I'm going to use this notation. I sub n is the number of inversion sequences of length n. So this is a way that that Juan likes to draw them. So instead of, so you can draw the inversion sequence 0, 0, 2, 1, 3 by putting horizontal steps at height 0, 0, 2, 1, 3. And then he likes to put this vertical step so it looks like a path. But basically what's important here is that this has to stay under the diagonal, which will be this condition here. Now, the reason these are called inversion sequences is because there's a natural bijection from permutations to inversion sequences where these entries count the number of inversions of the permutation. So the bijection is that, so you take a permutation and then you construct an inversion sequence by looking at, for each j, how many entries to the left of position j cause an inversion with pi sub j. Okay, so this will be counting inversions with pi sub j. For example, for this permutation 35142, you would look at how many elements to the left of these 3 are bigger than 3. So there are 0. How many elements to the left of 5 are bigger than 5? 0 again. How many elements to the left of 1 are bigger? There are 2. How many elements to the left of 4 are bigger? There's 1 of them. And then how many elements to the left of 2 are bigger than 2? There are 3 of them. So that's a bijection to inversion sequences, and that's why we call them inversion sequences. Now, now people for the last few years have also been looking at patterns in inversion sequences. And so with one, we've been looking at consecutive patterns, and the definition is again very similar. So an occurrence of a pattern in an inversion sequence is just a subsequence of adjacent entries that's in the same relative order. Now, the main difference is that now the pattern could have repetitions. So you could have an inversion sequence that contains a pattern like 0, 0, 1. The reason for that is that the inversion sequences can have repeated entries. So here 0, 0, 1, the first 3 entries here form a 0, 0, 1. The next 3 form a 0, 1, 2. And then it avoids 0, 0, 0 because there are no 3 consecutive entries that have the same value. Okay, so this is the definition, and then you can define again the set of inversion sequences that avoid the pattern. And then what Juan has been doing is he's been counting how many inversion sequences avoid each one of the patterns of length 3, and we have some recurrences. This is one of the cases. I'm not going to list a bunch of results, but just like, for example, for the pattern 0, 0, 0, there's this cute result that the number of inversion sequences that don't have 3 consecutive equal entries is equal to this formula that involves the number of the arrangements. Now, it turns out we don't have a bijective proof of this. So we can show that both sides satisfy the same recurrence, but there's no direct bijection. So if you like that kind of thing, you can think about this, how to find the bijection for this. Okay, now, you can define, again, equivalences between the different, between consecutive patterns and inversion sequences. And I want to introduce another kind of equivalence for which, so to define this kind of equivalence, we keep track of the occurrences of the pattern in the inversion sequence. And I just use this notation to mean that this inversion sequence, 0, 0, 2, 3, 0, 1, 3, has occurrences of 0, 1, 2, in positions 2, because there's one that starts in position 2 and one that starts in position 5. So I record the positions of the occurrences, and then we can define, again, consecutive patterns in inversion sequences can be Wilf equivalent if the number of inversion sequences avoiding one is the same as avoiding the other. We call them strongly Wilf equivalent if so this is the same as I had defined before, but now it's with this new notation. If the number of inversion sequences with k occurrences of one is the same as the number of inversion sequences with k occurrences of the other for all n and k. And now there's another kind of equivalence that we define that we call super strongly Wilf equivalent. So what that means is that not only the number of occurrences has to be the same, but the actual positions of the occurrences have to be the same. So these patterns are called super strongly Wilf equivalent if the number of inversion sequences that have occurrences of the pattern in a prescribed set of positions is the same as the number of inversion sequences that have occurrences of the other pattern in the same prescribed set of positions. So this is like a very strong condition for equivalence. And it's clear from the definitions that if they are super strongly Wilf equivalent, then they are strongly Wilf equivalent, and they're Wilf equivalent. So which one is stronger than the other one? Okay, so then we can do the same thing. Try to classify patterns according to Wilf equivalence. For length 3, this is the only kind of equivalence that we get. And actually, so I should say that for patterns in permutations, you get those trivial symmetries like reversal and complementation. There's nothing like that for patterns in inversion sequences, because if you take the reversal of an inversion sequence, you don't get another inversion sequence in general, or same if you take the complement. So we don't have any of the trivial equivalences. And for length 3, this is the only equivalence that we get. So these two patterns are super strongly Wilf equivalent. Now I guess I didn't motivate why we study consecutive patterns in inversion sequences. So, I mean, aside from the fact that other people have studied them, one of the reasons I think it's interesting to look at these is that there are some problems that people have looked at about pattern avoidance in permutations, that when you translate them at the level of inversion sequences, they actually become easier. It seems to be the natural setting to study them. So here's an example. This is something that had been studied by Baxter and Padwell, that they were looking at something called vincular patterns, and I'm not going to get into the definitions. Okay, maybe I'm very quickly I'll tell you. This notation means that 1, 2, 4 have to be consecutive, but 3 doesn't have to be. So it turns out these permutation patterns were conjectured to be Wilf equivalent, and then that was proved non-bijectively. But I think the correct setting to prove it is using inversion sequences, because it turns out that there's a bijection between permutations avoiding this pattern and inversion sequences that avoid these two patterns. And then once you have it in terms of inversion sequences, there's a pretty simple bijection to inversion sequences avoiding these two patterns, and then those become inversions, permutations avoiding the other pattern. So this gives like the right setting to construct the bijection.
Sure. So Sergey.
Yeah.
Serge, sorry. There's another question here.
Okay.
Grace was wondering if they use a code of a permutation instead of an inversion sequence. Do you think that might, I mean, is that a...
Yeah. So there's a couple of ways to go between the permutation to the inversion sequence. So yeah, so here when I talk about this this bijection here, there are other ways to do this bijection. So one of them is called the Lemmer code, and there are other like symmetries of it that one can use. And I mean, you can use any of them. Now, depending, there's actually there's a recent paper, I think by Megan Martinez, that she looks at different ways to do this bijection, and then how different parameters of the permutation translate to parameters in the inversion sequence. For most of the study about equivalence in Wilf equivalence for patterns in inversion sequences, it doesn't matter how you came from the permutations, but then when you have results like this one, these bijections, actually it matters which one you're using to go from permutations to inversion sequences. So this one is some variation of that theta that I defined, but it may be one of these codes or some symmetry of it. Okay, so now we have now we can also classify. So I said for length 3, there's the only equivalence. So we can look at equivalences for length 4, and actually it becomes pretty interesting there. There are a lot of non-trivial equivalencies for patterns of length 4. And here's the list of all the equivalencies. Now what I find interesting about this theorem is that all the equivalencies that we found are super strong Wilf equivalencies. So if you look at this, there's no two patterns that are just Wilf equivalent or just strongly Wilf equivalent. All of the equivalencies are actually super strong Wilf equivalent. So we weren't brave enough to conjecture that this will always happen. What we do conjecture is that if two patterns, I guess I forgot the W here. If two patterns are weakly Wilf equivalent, then they are strongly Wolff equivalent. And the reason we feel confident enough is because this would be the analog of Nakamura's conjecture for patterns in permutations. So we feel there's probably the same thing is happening for patterns in inversion sequences. So that's the conjecture. Now, conceivably, it could be, so I put these question marks, and I think probably this is not going to be true for longer patterns, but we don't have any counterexample. It could conceivably be the case that all three equivalencies are the same. Okay, so yeah, just a reminder, this one is saying that, so weak Wolff equivalence is that the number of inversion sequences avoiding one is the same as avoiding the other. This is saying that the number of inversion sequences with k occurrences is the same, and here that the number of inversion sequences with occurrences in prescribed positions is still the same.
Okay. Sergey,
yeah.
you got one more question.
Yeah.
It involves a little bit of notation. So we're kind of close to the end here. So I think that when maybe Darish, if that's okay, let's hold your question until the end when
Okay, yeah.
you look at it in the chat.
Okay, that sounds good. Yeah.
Okay.
Yeah. So in the next couple of minutes, I just want to talk a little bit about one place where consecutive patterns come up, which is in dynamical systems. So this was sort of, I mean, this was not the reason we started studying them, but then I learned, I sort of randomly, I met somebody who was working on dynamical systems. We started talking about our research, and I realized that really he was studying consecutive patterns. And so I'm just gonna try to motivate how that connection comes up. So here's two sequences of numbers in the unit interval. And I'm telling you that one of them is random, or at least random enough, what Maple considers to be random numbers. And the other is deterministic, in the sense that each number has been computed using some rule from the previous one. Okay, so if you stare at them long enough, you may have some guesses, but again, I'll tell you the answer. So it turns out the first one is deterministic, and each number is computed from the previous one, just applying this function. Okay. Now, there is one way. Well, there are different ways we could have distinguished them, but one of them is by noticing that. So using something called allowed patterns of a map. So the definition is pretty basic. So you take a map from a ordered set to itself, for example, the unit interval to itself, and then you take an initial point and iterate it. And when you get these numbers, you can consider the relative order, and that gives you a permutation. Okay, so we call that an allowed pattern of the map. For example, for this map 4x1 minus x, you could start with 0.8, apply f, you get 0.64, apply f, and then apply f. And then you look at these four numbers, and they are in the same relative order as 3, 2, 4, 1. So we would say 3, 2, 4, 1 is an allowed pattern. So if you do that, then you can define a set of allowed patterns. Turns out this set has some interesting properties, like it's closed under consecutive pattern containment. That's easy to see that if you have a pattern that's allowed, then any sub-pattern of it will also be allowed. And okay, so I'm gonna, since I'm running out of time, I'm just gonna say that so you can define the set of allowed patterns, and then there will be some patterns that are not allowed. We call those forbidden patterns. And there's an interesting theorem that says that for any map that's piecewise monotone, there will be some patterns that are not allowed. So for example, for 4x times 1 minus x, one could check that 3 to 1 is never obtained. So you never have a point x that is bigger than f of x and bigger than f of x. Okay, so, and there's a proof by picture of that fact. So, so going back to our original sequences, this is the theorem, but I'm gonna go in detail. If you go back to the original sequence, you could have seen that there were no 3 entries that were forming a 3 to 1 pattern, and then guess that that's probably because these entries were not random. If they were random, any pattern would eventually appear. So this is a very basic example, but this same technique can be used to create tests that are based in pattern containment that distinguish noisy deterministic sequences from random sequences. And in general, learning how many patterns are allowed for a given map, counting that using combinatorial tools is useful because that informs there are some properties of the associated dynamical system that can be obtained combinatorially. For example, something called the topological entropy of the dynamical system is now related to the growth of the number of allowed patterns of a map. So this is one way where these patterns appear in dynamical systems. Okay, and I don't want to go over time, so I'm just going to put the last slide. Thank you.
Well, thank you very much. So we do have, whoops.
Gary Greenberg has a question. Should we have?
Oh, I think I can see the chat now. I closed the slide.
Yep. Oh, you closed this. Okay.
So okay, see, I'm reading all the questions. So the last one, do they also have a connection with geometry? Wait, what has a connection to geometry?
Feel free to unmute yourself if it's easier than typing. Just don't everybody unmute at once. So, Praise, that was your question?
I mean, I don't know if the question is related to like how how pattern avoidance in permutations is related to Schubert varieties. Like, yeah, so I think nobody has looked at that. So yeah, we don't know if there's any characterization of properties of Schubert varieties that becomes nicer when you look at inversion sequences instead of permutations. Yeah, that's a good question, but I don't know the answer.
Okay, so scroll up, Serge. There's a question from Darish. I'm not sure if I'm pronouncing your name right.
Greenberg.
So at 257, so there's date stamps on the chat. So if you scroll up to 257, there's the question there that had some notation that I didn't want to try to read.
The one, how much does it matter that the inversion sequences come from permutations? Can you detach them from their motivation and generalize them to tuples? Yes, yeah. So these tuples where the bounds are not just like the ith entry has to be less than I. There's I think they've been studied too. I think Carla Savage calls them, I don't know, S inversion sequences or some generalized inversion sequences. And there has been some work about not so much about the consecutive patterns, but there has been some work maybe about with the classical definition of patterns, and they do have some interesting properties. So one of something that I actually was wondering, and I haven't investigated, but this conjecture about the Wilf equivalent being the same as strong Wilf equivalent, you could ask if that's true for these generalized tuples that you're describing. And it's possible that it's still true. I mean, my guess, without having done any experiments, is that it's still true. Now, luckily, before this video goes on the internet, I know that Bill can edit it, so he can remove this part if it turns out not to be true. But my guess would be that it's still true. There's nothing special about having these particular bounds on the entries.
We can also remove the joke if it's not a good joke. Right?
Okay.
So do we have any other questions?
Oh, there's I also asked, how many of your strong Wilf equivalents will still hold?
Oh, I beg your pardon.
Yeah. So, yeah, I think, well, I know some of the Wilf equivalences that we found were just happened because of the way the bounds are. So I know that they would change in general if you change the bounds on the top of the inversion sequence. I mean, I still think that the conjecture about Wilf equivalence and strong Wilf equivalence may be true, but the exact equivalences that you get will still change. I think what they will change. Another question: does the general solution to the differential equations you mentioned add any insight? So well, I don't, well, not to me. So I know that so for some of them there's some, for example, for the monotone pattern you can get some general solution, but it was, I mean, it's longer to state, and I just decided it was nicer just to give the differential equation. I don't know.
Any other questions? You can unmute yourself, or you can.
Yeah, thank the speaker. Unmute yourself if you want to turn on your video for a minute so we can see who you are. That would be lovely too.
Yeah, we like to unmute ourselves, both video and audio, for the applause at the end.
Yes. So,
ready, everybody? Okay,
yeah.
Thank you very much, Sergi, for
This was great.
Hey.
There should be an applause
Thank you.
button there. When you press it, it automatically applauds for you.